All right, so I got a question asking about a magnetic field of a solenoid. So let's just say we have this infinite solenoid here, and the question asks you what is the direction of the net magnetic field. To compute this derivation, we can start off by using a symmetry argument. So we can break down the magnetic field into this equation here, breaking it down into each different component. From here, we can use Ampere's law, which states that the integral of dl dot b is equal to mu 0 I enclosed. But what does this mean? So if we take a random arbitrary surface here with a surface charge density of Ko, delta S is going to be our path that we're going to be taking the integral on, and Ko is going to be equal to the current density, which is also equal to the current divided by the length. Ampere's law states that if we take the integral over the path, we can get the magnetic field for the whole surface. And so I just want to break down which each term represents. dl is going to be the small amount of path length, delta S is the total path, B is the magnetic field, and I enclosed is the current enclosed in the path. I want to note that it can also be written in this form, and this is due to Stokes' theorem. So you can apply Ampere's law to the situation. So this is our situation here, and we can start off with the component in the S direction. Draw our Amperian loop. We can use Stokes' theorem to convert it into a integral over the area. And so we can identify this as the small amount of surface area on our cylinder. The direction of dA is going to be equal to the magnetic field in the S hat direction for all points. The directions cancel out and we just get this here, so we can plug that in. And then now essentially looking at this integral, all we're doing is taking the integral over the area of the cylinder. So that just results in the final surface area of the cylinder, so we can just plug that in. Since the magnetic field is in the S hat direction, I enclosed is equal to 0, because if we look at our cylinder, all the current is in the phi hat direction. So if we plug that in, we get the final answer here. There's no field in the S direction. By the same method, we could find that there's also no field in the phi hat direction because the current is parallel. So if we look at our Z direction situation here, and then we draw our Amperian loop, which is going to be a rectangle in this case, draw our current pointing into the page, draw our dl direction, so it's going to be counterclockwise, and then our length of the loop is going to be L. The magnetic field can be broken down to the inside the cylinder and outside the solenoid. By our equation here, take the integral of paths S1 and S2 as we labeled up here, noting that the negative S hat and the S hat directions, the magnetic field is 0. So for this expression here, there's a minus side because they're in opposite directions. If we look at the closed current in the loop, it's going to be negative LKO inside, and then it's going to be 0 outside. The negative sign is due to the direction of the current, and it's LKO because of our equation for KO. Plug this in. BZ at S1 is going to be equal to 0 because it's an infinite solenoid, and then we get this for the final answer. This is going to be the magnetic field in the solenoid, and there's going to be 0 magnetic field outside the solenoid. So we can conclude that the magnetic field points in the Z hat direction.